Okay, assignment number 3, Mathematica. Wow, how did this happen? This is interesting. Okay, so please pay attention. This is what the answer should look like. This is not the input. The input is all scrambled, all messed up, and I want you guys to go to this stage. Do you have questions about this? Yes?
Yeah, quotes. Do we need to? Because in this array we have, this is a real number, yeah, in the left.
Mm-hmm.
First element is real number,
Yeah.
and the second one is string.
Yeah, it's a string, yeah.
So when we do a string, should it be with quotes as an output, or a
Yeah.
string without quotes is okay also?
That's the same. A string in Mathematica needs the double quotes.
I do an output and I have just without quotes. Maybe there is some function which outputs me quotes.
As long as it's a string, that's fine.
Okay.
It's like when you copy it from the output, it's unphrased, and otherwise
The strings. I didn't think of that. I have to check what my solution does. What I care is that this thing is a string. If it comes out as a string, then it's fine, with or without quotes. As long as it's a string. Other questions? So the file is accessible, right? Yes?
What does it mean? Cut the name of the clause?
So if we go to that web page, you see that each name is much longer. It has some, it's not garbage, it has some extra information after the number, and I want you to cut all of this knowledge at the number. Okay? So that was easy, or at least this is supposed to be easy. Second, this is not so easy, but it's not too complicated either. So we have input, we have a number of arrays, k arrays. They might be of different length. So it's not a list of lists of the same length. It's just k different arrays. And then we have an integer that has nothing to do with the arrays. These are completely separate pieces of information. What we want to do is to assign the elements of these arrays to p different processors. All right. And I have one entire slide to explain how the assignment works. So these are the input arrays. I used 4 different colors for the 4 different arrays. As a first step, we have to sort all the indices, all the entries. So we have to sort them together. And I maintained the color to identify from which array they're coming from. Then I split this array in as many pieces as processors. Not only do I do that, I also want these pieces to be balanced. So I want each piece to differ from another by at most 1 entry, in number, of course. So if I only have 3 processors, the first guy will take 5 elements, the second and the third guy will be responsible for 4 elements. If I have 5 processors, okay, the first 3 of them will take 3 elements, and then the last 2 will only take 2 elements. What I'm showing here is that this is not a good assignment because 4 processors take 3 elements and the last one only take 1, so there is a difference of 2, so that's not good. It means that one of these elements needs to be taken care of by the last processor. Okay, so once I have done this assignment, I have to scramble back. So let's see, the number 1 blue, okay, since it's blue, it means that it came from the second array, will be taken care of by processor 0. So here we put a 0. And it's a position that tells me that this refers to 1, because up here there was a 1, and so now 0 is responsible for 1. If I look at 4, Okay, the answer is 1, which means that processor. What? If I look at 4.
This is P equals
Oh, yeah. Thank you. Over here, it's 2, which means that the second processor is responsible for that, and that's exactly right. If P equals 3, 1, and so I go 1, and 4 blue is here. Okay, and so on. And I want you guys to implement all of this in Mathematica. And as before, no while loops, no for loops, no do loops. I didn't even introduce do loops, so don't even think about those. No tables, and yes, all of the following. Questions about this? So maybe the one question that you guys should have is, I said that this configuration is not good, and I need one processor to, let's say, donate his extra element to P4. So one question is, should always be P3, so like that, or is it okay if P1 donates one element to P4? The solution is considerably easier if you allow these guys to donate. If you force to be the last processors to be the ones with the fewer elements, the solution is more difficult. Did you understand that point? Not really?
Does difficult mean slow?
No. In terms of programming. Okay? Number 3. This is a beautiful game that I came up with last week. I will play myself this game, okay? I will compete against you guys. So, what do we have? Maybe the easiest thing is just to show how the game works on board. Let's start with an integer. Maybe, well, I wrote 42. Let's say that this is the starting point of a sequence. So it's the first entry. What will be the next entry of the sequence? Okay, I go and look, I count how many of each digit of, how many of each digit between 0 and 9 are in this number. There are no zeros, so nothing. There are no ones, so nothing. Oh, I find 1, 2, so I write 1, 2. Now, look at that, I find 1, 4, so I write 1, 4. All right, we iterate. How many ones do I find? 2, so 2 ones. Then I find 1, 2, and 1, 4. Notice that even if the first digit is a 4, I put the 2 in front. This is very important to get a convergence. If you just say that from 4, 2 you go 1, 4, and 1, 2, this is not going to work. This sequence will diverge. So nope. You always have to go incrementally. So what's the next? Here we don't have it. What's the next entry? We have 3 ones, then 2 twos, and 1, 4, and so on. Is this clear? Good. Well, so that's as simple as that. I want you guys to use this piece of code to study the evolution of the sequence. The sequence might converge, might enter a loop, but that's irrelevant, that's not important. What I want you guys to write is your own function that takes one entry element of the sequence and spits out the next. So what was the question? Somebody had a question? No question? Yeah? Go ahead. I made that up because I didn't know how to. So this is just way of saying that I take some digits and I put them together. Square brackets. Here? Oh, I want name to be your name, so that I know who wrote this function. That's it.
My guess is that it will converge about 2 or 3 iterations after it reaches 9. Is that even close?
Again, I don't. It's not important to understand how this sequence behaves. Okay, guys. So far, so good. Yes.
So our rule function just takes the one number from the sequence and
Spits out the next.
and
Yeah.
that's all.
That's all.
Just again takes continues.
No. The whole thing is done by fixed point list. I want you guys to write a function that can be plugged in here. So you should test your function with this piece of code. You put rule of Paolo inside, and you see if it does what it's supposed to be doing. All right? So now, this is the fun part. I want you guys to write 3 versions of this function. The first one, it's called the rule of Paolo, or whoever you are, and does not have anything else but replacement rules. Nothing else, 0, okay? The only exception is block, okay, just to block some variables for the patterns. But the whole thing is done through replacement rules. Needless to say, this is going to be slow and long, but also very simple, I think. Then we have the fun part, and once again, this is purely for fun. And I will challenge you. I came up with something pretty short, so I don't want to say the number, because otherwise maybe you are intimidated and you don't even try. But I came up with something kind of short. And then we will go for something fast. And when I say fast, I mean we will pass a large number, and we will see how fast it can compute the next entry in the sequence. Okay? Yes.
Megabytes?
I don't know.
Okay.
I don't. I don't know. So, since these are challenges, all the winners, the 2 winners, get a bonus. I told you already. And I'm thinking that if you beat me, maybe you should get a special bonus. So I'm still thinking what I could, how I could pay you back in case you beat me. I don't think you will beat me. At least for the length. I don't know for the speed. I didn't spend too much time on the speed, but for the length, I did some advanced stuff. All right. So. Just one more time, please submit by 1 p.m. Do you guys have questions? Yes?
In challenges, it's not only replacement rules.
No. Challenges, you can use anything. Feel free to use for loops and tables. Be my guest. You will.
Does Mathematica have some kind of assembly language?
Oh, that's a good point. It has to be a Mathematica construct. You cannot call a C function or anything, or an assembly. No. So you have to stick inside the realm of Mathematica. Thank you for asking. Yeah.
What's the objective for the first assignment? Is it speed or elegance? For not for this, but the part of the tones and this sorting.
Absolutely not speed. Speed is not an issue. And this one here is probably elegance. Yeah. Again, speed is not important. I'm not going to test this with super large arrays or very large k. So no. This is not even a challenge. So this is just for you to get some coding. Yes. Nothing? All right. Then if we're done with this, I think I can go through the exercises. I know that somebody tried them out, so let's go through them. I think this could be helpful for you guys for the homework. From where do we start? Write a one-liner that returns, okay, let's start from that. That's super simple. Frequency of pi. So here's my solution. Maybe it's not so easy to look into this like that. Let's start from a piece at a time. This is clearly something that takes a list of digits, creates a list of digits. There is an I, so clearly I need an iterator somewhere. Okay, and here. I think it's here. Probably is this really that large? 10. Okay, yeah. So what do? I put, that's what real digits does, take a number and creates a list of the digits. So the first entry is, oh yeah, now I remember. This is very annoying because it tells me also how many digits are before and after the dot. And that's why I take first over here, which means I only look at the digits. First. Okay. Then what do we do? Yep.
Execute that, please. Yeah.
Thank you. Yes, so that's not at all what I meant. So first real digits, it's inside the table. How about that? Yes, this should work better. Okay. So far, so good. I did something. That's what I want. All right. Then I drop. I have no idea why I'm dropping. What am I dropping? What am I dropping? I drop. Okay, I don't know why I'm dropping. Maybe it's to drop the 3. Probably it's to drop the initial 3. I don't know why I'm doing that. Drops -1. No, I don't drop the 3. So what did I do? Ah, you know what? Look at that. This is interesting. I think so. If I don't drop 3, 6, yeah, exactly. So for some reason, exactly. This is 11. That's why I drop. That's 11. Okay, that's why I drop. But why did I put 1 then? Oh, this is for the rounding. Ah, I see. So I ask 1 extra digit and then I drop it. Because otherwise, if I didn't ask for this, the last digit would be rounded and that would not be meaningful. So I ask for 1 more and then I discard it. Wow. Clearly I didn't do this year, right? So that's why I drop. After that, we count. This is easy. How do we count? Count takes a list. In this case, again, count should be inside. Count takes a list as a first entry. That's what we have here. And then it does something with this list. It counts how many times a certain pattern appears. So inside the count, I should put 0 and 1 and 2 and 3. So over here I should have maybe 0. And this would give me how many times number 0 appears in the first 10 digits of pi. It appears never. So in the first 100 digits appears 8 times. In the third 1000 digits appears 93 times. Okay, but now we would have to do this for 1, for 2, and for 3. So why don't we just map this function to all the digits from 0 to 9. And this is easy. Range creates a list from 0 to 9. So what is it? So here, count, there is an error, but I don't know where it is. Have to, here. Okay. Not okay.
There's a slash at before range in your solution below.
I didn't understand. Say it again.
In the solution below, in the lower solution, there's not the usual pattern. The replacement rule is slash at, not slash top.
Oh, so first of all, it's this. Thank you. That's what you meant, right?
Yeah.
Yes, but there is still a problem with parentheses. So, this is 1. This is real digits. This is first and this is drop. Okay, so far so good. Then count. Okay. So count, this is where I have to count, this is what I want to count, and this is I apply count to that guy. So far so good. Okay, and this is the frequency, no, not really, this is the total number of appearances of digit 0, digit 1, digit 2. Okay, now we can repeat it, and we have, this is for the first 10 digits, 100 digits, and 1,000 digits. Okay, so far so good. But I didn't want the total number of occurrences, I wanted the frequency, so I have to divide this number by the size of the list, and this is the size of the list. Notice that if I don't put the dot, I get these things. So I add a dot and I get frequencies. Okay, that's more or less enough. This would be already enough. Now we can beautify it, adding a first row with the actual digits. We could further beautify, a first column. We could further beautify it with a first row, but that's okay. Okay, so this was easy, right? Questions about it? Does anybody want to show something else? No? I think the most important part of the exercise is something that I didn't ask you to do, which is this instruction here. So this is the challenge for you. What is that thing doing? Notice T is almost to this old beast. It's before the table form. So, and that's over here. So what is that instruction doing? Come on, that's
What does rest do?
rest is the, we used it already. Did we? No, we didn't. We used the first. It's the CDR of Lisp, which means everything but the first entry. Yeah.
So if we have this table there,
Yeah.
beautiful,
Yeah.
and it consists out of columns, and your method sums up all the columns.
Whoa, whoa, whoa. A table or a matrix in Mathematica goes by rows. It would be nice to have it by columns, but that's not the case. Matrices are stored by rows.
But I thought the T to the power of T transposes it.
Yes, but you didn't say it. You're right.
I wanted to.
Yes.
I
So,
wanted to present the final result.
all right. Okay.
So okay, it transposes it, and then it sums up all the elements, and disposes the first element, which is the sum from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This goes away, and everything else is summed up.
Yeah, you're perfectly right. So, explaining the pieces. This is the column and it's transposed. So now you imagine that instead of going by rows, on the first row there will be these numbers, on the second row there will be these numbers, and so on. That's what happens here. And what do we do here? We take this function and we apply it to each of those rows. So, and what is this function? Is plus applied to the parameter, to the argument. So we're doing nothing else but just adding all the entries of the argument. So we are summing by columns. And why is that important?
Everything should be 1.
Yeah. So I don't want to make fun of anybody, but last year a student came for the oral exam and he showed me this assignment and he had 0, 0, 0. And so I'm like, what does it mean that there are zeros down here? Probably means that, does it mean that there are no 9s in the expansion? So, well, he didn't have this column over here actually. So his last entry was not 9, but was the digit 10, 1, 0. And of course, it never showed up. But you know, whenever you do something, that's the moral of the story, you should always, always have a way of testing your result. And so in this case, you should add by columns, and if it doesn't add up to 1, probably there is something wrong. Okay.
Can you show full form of this last statement of the object?
This?
Yeah.
Why? What else did you
No,
expect?
I wanted the function actually, and not the result. The full form of this plus add.
Okay? So, lesson to be taken home, always find a way of testing your results. Here. I don't know, actually yes, I have a lesson for this example as well. I worked on this recurrence. So this is how I implemented this. By the way, do you guys know what it's supposed to be doing? We have this recurrence sequence. We start from a given x0, y0, it's a point in the plane, and x1 and y1 are given by this function, and then x2 and y2, and so on and so forth. Always applying this recurrence rule. These recurrence rules relies on the previous x, the previous y, so the previous point, as well as 3 parameters a, b, and c, and they are fixed for the entire sequence. And I gave you a few starting points, a few configurations to test the function. Did anybody try? I got somebody sent me an email that. So what did I do here? Since we have to iterate, we have to apply function to a starting point. It spits out another point. Then we want to apply the same function to this output and generate another one, and then we apply the same function over and over. So since we have to apply the same function over and over, for sure we use nest, but since I ask you to create the full list and not just the end point, I want to see how the list expands, then you use nest list. Okay, nest list, we have a function as a first entry, and then we have the starting point and how many times we want to apply the function. And the function is a function of 2 parameters. So since I'm working with 2 points, that's why I have curly braces. I put together the x and the y. This first part belongs to the x. So what does the x do? We need the y, we need the x, we need the x again, b, c, square roots. Okay, we need the y, and the y, what is it? It's the second part of the argument, because even though I'm working with 2 numbers, x and y, with 2 parameters, the argument is actually just 1. It's a pair. So in order to access y0 or yn, I have to access the argument and then the second part of it. In order to access x, I access hash and then the first part of it. And then I do the math that I have to do, that's fine. Okay, how do I create my yn? This is easy, a minus xn, and here it is, a minus hash of 1, so xn. Very good. So this creates the next point, but I want also to plot them. And this is the part that you guys probably wouldn't have any clue on how to do, because we didn't look into visualization yet. But this is a way of creating a point in the space. There is the primitive point, and it takes an x and a y. Actually, it takes a pair. So we literally have to do nothing more but just adding point to all of these entries. So it's easy. I map point to this list. Here I specify the size, and the graphics is something that plots, that puts on the screen all this list of points. Okay, and I put all of these inside a function. Let's start with few points. Let's remove the timings for now. Okay, looks like it's working. At least I have some points in the space, so it looks like everything goes fine. 1,000, nothing much is happening. 10,000, it should be already visible. It's a pretty image. And This is a bit of a clutter, I think. But it's a good way of, 100,000 is a good way of testing the speed of your function. Except that my Mac is dying. Okay. So far so good. Now what I want to do is to time this object. Okay, and it takes 0.1. Did you notice the difference? So computing takes almost nothing and plotting took several seconds. So what I did, which probably was not so intuitive, yeah.
Do we have the problem of we calculated already and then we calculated again, so he cached it?
Not, I don't think so. But this is, see, this is purely the visualization thing. Okay, something that you guys maybe wouldn't have done yourself is to use a pure function to handle all of these mass at once. Probably the first thing that you guys would do is to define your own function that has ABC as parameters and x0 and y0 as arguments, and it would return that. What's the difference? Zero difference. These things are exactly the same thing. It's just that one is a properly defined function with a name and arguments, and another one is a pure function which you cannot use anywhere else but right there on the spot. So if you define your own function like this, which by the way is a good way of starting an assignment, so going right away for that it's probably not a very good idea. Then what do you have? You have the same story as before, except that now you have a nice clean call to my function. ABC, they never change, so here you go. In fact, we could even remove them, or okay, let's just leave them like this, and these are the two arguments. Okay, so if I did that, do you think this is going to be faster or slower? By how much? By a little bit or by a lot? This is about 10 times as slow. This was 0.12, this is 1 second. So it's about 10 times as slow. They are doing the exact same thing, okay? It's just that, of course, this is a proper function. Every time it's invoked with different arguments, and the other one is a pure function, so interpreted in a different way. And, well, since we're here for having fun, we can look at different configurations. 1, 4, 1, 1, 2, 2. Point 299. Oops. 0.299. All right, and we have different things. This is not very pretty. Okay, I guess you guys can play with it. Let's move on.
There's a simpler way to plot it. There's a function called plot list, so you don't have all this extra stuff.
Ah, plot list. Yeah, I guess you can use plot list in this case. That's a good point. Let me see. I didn't even think about plot list for this particular case. No.
It's list plot. Oh.
Thank you. Yeah, I guess it's the same. We have to do maybe some, we have to pass some parameters, but I guess it would work. point size and whatever axis would be false. Yeah, I guess we could get to the same answer. Thank you. Yeah, good point. And also maybe we want okay, so now we have the same aspect ratio on the x-axis and the y-axis. Let's continue. Okay, this is really stupid. It's just to have a one-liner. So what do we have to do? We have to put together, in case you have not read it, sorry, you have to put together all the numbers between 1 and 1979. So 1, then next to it you put 2, then 3, and all the way to 1979. So it's a really, really long number. And then you compute that modulus 1980, whatever, let's just do it. So all the numbers between 1 and 1979, we do it with range. That's what range does. Then we transform each one of them into integers. So this is a map. I'm sure that by now you recognize it. So integer digit applied to each of these numbers. And so now I have a list of digits for each of these 1980, yes, entries. No, 1979. Yeah. And so, okay, so far so good. Then I put them together with a join. Join can be applied to not just two lists, but multiple lists. So that's why I apply it to all of these lists at once. So after this, I have a really, really long list. Then I transform that into a number, and I have no idea how long this number is. And then I compute the modulus. So super stupid, but it lets us use mapping and maps and apply. Map and apply. Here we go. I don't really have any comments on this. So let's go to maxima. Maxima is kind of fun. Let's go to the last one, then we look at these ones later. Maxima. What we want to do is basically we have a landscape of numbers from left to right. We scan these numbers, again, from left to right, and we want to identify the maxima. So every time I find a peak, let's say that it's a mountain, a peak that is higher than any other peak I encounter on the left, I take note of it. So in this particular case, the highest peak is right on the left, everything else is smaller, so I only report the highest. Over here, okay, 1 is the first entry, and the leftmost entry is always a maximum. So we have 1 as the highest peak, then the next one is higher than 1, so I report 5 as well. 3 is smaller, 2 is smaller, 4 is smaller, but 7 is higher than my highest peak, so in the end I have 1, 5, 7. And if I have a sorted list, of course, I get each individual entry from left to right. Yes?
We will use something like REST again.
We will use REST. Will we use REST? I guess we could use REST with a recursive call, but I will only use replacement rules. So no REST for me. Maxima. And this is my rule for maxima, replacement rule. So what do we have? By now you know very well what this is. I am selecting two consecutive numbers. I have any number of entries on the left, any number of entries on the right, and I am selecting two consecutive ones. and I'm only considering the case when my highest peak is larger than what I just encountered on the right. If that is the case, it means that my element on the right is useless because it doesn't beat, it doesn't surpass my current peak. So what do? I just discard it. That's it. Questions about that? And I repeat this as many times as possible. Yep.
Basically, the lower item just gets discarded.
Precisely. The idea is to get rid of the items that I don't care about. So this list is shrinking until only the big items remain. Well, there is a little bit more than that. There is also the fact that in a way it's discarded, but I'm still looking right. See, I select two guys, two consecutive entries, and I discard the one on the right. So there is movement. Okay. So this is the list. And this seems to be working perfectly. So all these guys are discarded. Then we end up to -2 and 5. 5 is greater than -2, so it's not discarded anymore. And it will not be matched anymore. Because over here, two things are matched only if V1 is larger than V2. So since now -2 is not larger than 5, these three guys will be gone, and -2 and 5 will not be matched anymore. So now my V1 will become 5. Oh, and will be replaced right away because there is a 7. Okay, then 7 will become, let's say, the pivot. And a long list of, actually not so long, 2 comparisons will happen, and then 18 will take over, and okay, there will be a list of comparisons and so on. Okay. Questions? If not, I want to show you, I think probably faster. So let's do some timing. I shouldn't go in steps of 10 because this thing is not linear. So this is dangerous. Okay, 20,000. Okay, what is fold list? Fold list comes from fold. Fold is very close to nest, but not quite. In the nest, we have a function, a starting point, and a number that tells you how many times the function should be applied to itself, and with x as a starting point. In fold list, I have as a third argument, I have a list which tells me how to compose the application of output of f of x with f. So I start and I say x, then f of x of a, then the solution of that, it's here, it's applied to together with b, then this whole thing will be applied with c, together with c, and so on. So, if you look at, let's take something here. If you look at these numbers, if you look at maxima, basically what am I doing? I am always comparing two numbers, two adjacent numbers, trying to find which one is larger, which is the max function. So let's take this. I go from 1, and 1 by default, it's the leftmost, so it's always a maximum. So, no comparison, 1 just is there. Then I compare 1 with 5. Which one is the maximum? 5. Okay, then I put it there. Then I go 5 and 3. Which one is the largest? 5. Okay, it's there. Then 5 and 2. 5 wins, so I put it there. 5 and 4, 5 wins, so I put it there. 5 and 7, now 7 wins, so I put it there. In the end, if I eliminate the duplicates, I get the exact list. So let's start from a small small list. This is what I'm doing. Okay, it would be nice to look at the list. Initially, fold list puts the starting point, which I set to minus infinity. Why do I set it to minus infinity? So that I'm sure that I don't put a number that is larger than something inside the list, okay? It's a starting point. And then I compare minus infinity with the first entry. And of course 14 wins. Then I continue and say 14 and 7, okay, 14 wins. And then the result, notice that it's not that I am marching. It's not that I'm moving instead like this with a window. It's not like that. I take the result of the previous function and I apply it with the next entry of the list. So what do? I do maximum between minus infinity and 14, and the answer is 14. Then I say maximum between 14 and 7, and the answer is 14. Then maximum between 14 and 16, and now I switch. See? 14, 14, and now I use a 16. And then maximum between 16 and all of these guys until I get to 20, and here we go. And 20 is the largest. So at that point, I only need to get rid of infinity, and I will use rest as suggested. And then I have to get rid of all the duplicates, and for that I will use union. And this is the answer, or union rest. So now we do some timings for this as well. Why did I go for 20,000? Okay. And you see that there is a little bit of a difference between replacement rules and functional programming. Replacement rules are cool, but don't expect anything fast out of them. All right. Yes. Yes.
Maximum does the now I got it. I read maximum instead of max. So I wonder, two arguments for maximum, strange. But if it's max, then it's okay.
Okay, given a list of complex numbers, sort them in increasing order according to the real part, and then in decreasing order according to their imaginary part. I don't think we really have to do this because we saw already how to do sorting with replacement rules. So that's how to do the first part according to the real part. And then it's just a matter of adding an extra constraint. So first we sort according to the real part, then we put a second replacement rule for the imaginary part, and over there we have to, as a constraint, we have to set that the the real part is equal. So I only apply this as second statement if the real parts are equal. Otherwise, there is no need to sort according to the imaginary part. So let's not do that. And instead, let's work on this, which is a little bit more fun. What do we have? We have a list of replacement rules. And that is the input. And what we want to do is to identify the cycles within these replacement rules. These replacement rules are special because they represent a permutation. Basically, we have all the indices from 1 to n, and they are mapped to other indices, but again, only from 1 to n. So it's a permutation. And I want to see if there are cycles inside this permutation. So how to do that? And of course, we use replacement rules. What do I have here? First of all, we need a way to generate something like this. So I need to create the input. And for that, I found a random sample. Random sample simply shuffles the list. So I create the entries from 1 to n, and then I shuffle them. Okay, that's, yeah. And then what do I want to do? I said that this is a permutation, so I want to write out the replacement rules with 1, 2, 3, 4, 5 on the left-hand side, and then the arrow, and whatever the random sample tells me on the right-hand side. So for that, I use map indexed. The function that I apply is this one. Let's see what it does. Actually, can you guys see what it does? What is this object here? Precisely, yes. And do you know what the second argument is? Yes, notice that it's not map, it's map indexed. So
map index put together the input with the number incrementing.
Yup.
So the second argument is the index.
Yep, you're absolutely right. So map simply takes the argument, but map index does much more. It catches the argument, here we go, as well as the position of the argument. So this thing over here goes inside the second entry and takes the first part. So basically takes exactly the number. For the first entry, this is a 1. For the second element, this is a 2, and so on. And then it creates a replacement rule towards the first argument, so the element that comes from the shuffle. So if I do that, I get a list of replacement rules. Notice that this thing over here is a replacement rule, but I don't apply it, so that's left unevaluated. Okay, and then what do I want to do? So we have this list. My idea is, what is my idea? First of all is, basically I want to apply these rules to the left and to the numbers 1, 2, 3, 4, 5 to see how they evolve. Basically, I want to build the cycles. So how to do that? I start off by deconstructing these rules and just creating a pair, 1, 1, 2, 4. Why am I doing that? Well, basically, I'm starting creating these cycles. So at the first iteration, I want my list to contain, let's say, 1, 2, 3, 4, 5. And then I want to apply all these replacement rules so that 1 goes into 1, then 2. But since 1 goes into 1, okay, I want to build lists. Then number 2, I want to go into 4. Then number 3, I want to go into whatever it is, and so on. This is the first iteration. Then at the second iteration, let's do it here. 1, 1, it's a cycle already, so I don't want to continue. But 2 and 4 are not a cycle, so I want to see where 4 goes. And 4 goes into 5, so we add it. Then 3, it's a cycle already, so we stop, and so on. Okay? So how to do that? First of all, I decompose the rules, which means I have performed one step. And then there is nothing much to do. I just apply the rules, more or less. So I check whether it's possible, so whether I have a pair, AB, and another pair so that there is a B in common. So if I have 2, 4, now I want to know where my 4 is going. So I want to look at a pair that has a 4. And if such a pair exists, well, why don't I merge everything together? Because I know that these two cycles will be joined. So this is to match anything. This is to match a cycle that I am building. This is to match something in between. This is to find an entry that has a B. So since this cycle terminates with a B, I want to find the rule for the B somewhere else. And this is to match anything. And every time I find that, I just put all of these guys together in the cycle ABC. And then I put M and R, I put them there. Okay, we don't need this yet. This doesn't look good. Did I assign something to? Not good.
L is used as the list from before,
Probably
because L is a different color.
L is used. Huh? Ha ha ha. So I think I have a clear somewhere. No, I don't have a clear. Dangerous, dangerous. Clear A, B, C, L, M, R. Anything else? Okay. So I have created my cycles. Nice. But I don't want to have these repetitions, so I want to discard. So here we go. I deleted my rule, of course. So what do I want to do? Every time, let's see. Maybe let's put something else. E for ends. Every time I find two, well, the beginning and the end of a sequence, I need more. No. What did I do?
There's an L before.
Ah, thank you. Here we go. Okay, let's try something larger. And any other cycles. And notice that the rules are applied, that the precedence of the rules is from left to right. So first this repeated replacement completes, and after that is done, this replacement happens. Questions? No questions? Then we're pretty much done with Mathematica. I think we can just, we have 20 minutes, maybe I can do a little bit of a visualization. And then we will finally move on. Okay, let's do visualization. We have a function that creates a list of points, sine of cosines. Here we go. This is very much what you would do in MATLAB. Every time you want to plot something, you actually sample and then you plot the points. And over here I would use list plot. The way of modifying, changing, editing, formatting your graphs, your figures is by options, through options. Gazillion of parameters, all of them are replacement rules. So, for instance, what if I want to have the same aspect ratio on the axis, on the x and y axis? That's aspect ratio. What if I want to join the lines? What if I want to filling? Oh, this is a little bit crazy. What if I want to do this kind of shading, filling? These are the three curves of that family of curves. Okay. We can go in 3D. There is graphics and graphics 3D. I showed you graphics already. This is graphics 3D. I can show you what this is. This is just a tiny little sphere. Okay, it's not so tiny here, but. And over here, what I tell Mathematica is that I will use M, so that sphere, as a plot marker. So here I had points, but I didn't like points, so instead I will use the result of this other graph, of these other graphics, as a plot marker. And then since I want to specify parameters, different rules for all of these three different functions, I generate three separate plots. I inhibit the output with a semicolon, see? And then I put all of them together with show. Actually, I don't know why I don't plot the first one, but here we go. So now I put two of them together, and you see that now there is my sphere, which is the result of another plot, and you can just keep putting things together, no problem. Here is a way of looking at the function that we just defined. So if we give a value of 1, this is the function. If we give the value of 2, this is the function. 3, 4, you see that the points are getting more and more sparse. So maybe we should do something about it. Okay, another thing is there is a difference between integer steps and real steps. So over here I specified that the increment should be in steps of 1, so that's why we can only go 1, 2, 3, 4. But here we'll see what the function looks like for any value. But again, the points are getting sparse, so we should do something about it. So a possibility is to pass an extra parameter that specifies how many points we should use to sample the function. And now I can have two sliders, or one slider and whatever fixed. And when the thing is getting too sparse, we just add more points. Okay, maybe this is a little too many. Okay, you got the idea. This is a way for plotting lists, matrices basically. List of lists, actually. This is not a good way of plotting matrices. This is a way of plotting list of lists. Okay. Let's go to a function. Best way to plot a function in Mathematica is simply asking Mathematica to plot the function. Forget about sampling. That's what Mathematica is good at, so let's just use it. And we could, for instance, I showed you this already, we can solve, we can find all the zeros of the derivatives. So this is a way of identifying maximum and minimum. And this is a way of plotting mapping the point to the solutions. And then we can put everything together again with graphics and or show. Oh wait, show, here you go. So now I have one line for the function and one line for the points. The points I've created there, put everything together, and I identify the maxima and the minima. I could change the function to compute the zeros of the derivative. So reduce is a more general function. It doesn't return replacement rules, it returns equations, well, okay, solutions, general solutions. So now I can plot all the zeros, not just the zeros within an interval, but all the zeros. And how do I do that? Well, okay, it's always the same story. I have plot, and then I put things together. In this particular case, I don't use show. I could have used the show to create a plot for f and a plot for the points. Here I want to show you that I can do this in different ways. I can use my epilogue or prologue. And what do? It's always the same thing. I map points to a list of solutions, points, and then I put everything together. Okay, I don't remember what this is. I guess I'm just changing, oh yeah, I'm just editing the points. So I can pass directives to edit the formatting. Okay, let's do something a little bit more fun. Let's say that I want to plot the tangent to the function. So here I have a function that takes some function. I want to plot the tangent to this function f in the point x0. And in order to plot the tangent, I will have to put a line. So h simply tells me how long this line will be. Okay, x0 will be the x-axis, y0 is the evaluation of f, so it will identify the point where I will display the tangent. M tells me, f prime of x0 tells me the slope, and over here I use another directive to create a line, and this is pretty easy. Line takes a list of 2 points. Here we go. So now I can plot, I have my function, and then as the epilogue I invoke the function tangent, tan of the function f in 1 point and with such length. And here you go. Maybe I want to know the slope, so here is text is another directive to add some text. So not only now I have a list as epilogue. First entry is the line, and the second entry is a text that tells me the slope itself. Oh, and by the way, I put some manipulate so that now we change things. So here is the slope. This is the length of the line, and this is the point. So that it just move by itself. All right, so this is super fun, of course. Now you see that there is something that maybe we don't appreciate too much. You see that this thing, the length of this thing changes. This is from the way I defined, by the way I defined this tangent. So over here I have my way of defining a second way of defining a tangent, fixing the length. What was the problem in my tangent definition? I say that I go from x0 minus h to x0 plus h, where h is the parameter that I pass, which means that this tangent has always a fixed horizontal distance. So it doesn't matter where I am, horizontally, this is always of a certain width. That's not the right way to do it, so how should we do it? Here is how I define the distance of 2 points. Well, it's the Euclidean distance. I compute the distance of, whoa, clear M maybe. Let's try again. Okay, here I compute my distance. And here I impose that my distance is a certain parameter, so I solve. Okay, get the solution in K, and now my tangent 2 doesn't do minus h plus h, but does do minus k plus k, where k satisfies that equation. Here we go. Now we redo the whole thing. Whoop. Ah, much better. Now the thing stays constant. Okay, let's continue super fast. How about adding a ball, so a disk? Now we can, okay, we don't need this. We can do straight here. We can create our function. So I put some parameters to play with the function. What are these parameters? The function is a polynomial in a sine polynomial. A, B, and C are coefficients there, okay? And then I have my point that will happily go through the function. Okay. What's the point of all of this? It's very, very easy to create animations or to verify ideas. If you have some ideas, if you want to create a demo for your project, for your demonstration, it's super easy to do that in Mathematica. Notice that I'm not trying to sell Mathematica to display, to plot data points. That's not the right object, the right tool. MATLAB is much better to plot data points. But to do 2 and 3D visualization of physics or animations, demonstrations, Mathematica is infinitely better. Okay, I guess I can conclude with a little bit of a smartness. I want to show you how Mathematica plots functions. So we have a function g, and this is, if I simply ask Mathematica to plot it, that's what it comes up with. Normally, if I don't know what g looks like, the best I can do is simply sample the function and then build the line connecting all these points. So I would have a list plot and then join the true. Here we go, and you see that the two things are not at all the same. You see how brutal this is. I can put things together. As I said, you can use a show. One is a plot, one is a list plot, doesn't matter. I can put everything together. What I'm trying to display here are the areas where the two lines do not overlap nicely. So that's these yellow parts. Okay, and now I want to show you how Mathematica evaluates a function. So I define my function in g_aux, so function g with auxiliary points. What the function does, well, it evaluates g, nothing else, but every time it evaluates g in a point x, it drops the point x into this big bucket called evals, evaluations. So every time I call g_aux on a new value, this new value is added to this list of evals. Notice the trick that the function does something, but then in the end it returns the value of g, okay? So now, in case you lost me, g is this function, g is this function here. And I want to discover how Mathematica comes up with such a smooth, nice plot. That's the goal. Okay, and now I ask Mathematica to generate a plot, which doesn't come out very nicely because I didn't evaluate Gox. Okay, so when I ask Mathematica to plot Gox, of course it plots G, but it has done something more for me. It has now collected all the evaluations of the function G. So now I can go and look at where Mathematica evaluated the function. And look at that. Here there are no needs of evaluations because the function is basically a straight line. It realizes that. But where the curvature is greater, lots of evaluations there. So now I can put things together, and this is what the function looks like and where the function is evaluated. And I will conclude doing the same thing in 3D, and 3D is much more interesting actually. Okay, I chose a function that is a little bit nasty so that we see something. Notice the same way as a plot, now we have plot 3D. Same way as before, we had a function. Well, before we had one parameter, one argument, now we have two. Before we had one iterator, now we have two, and that's everything is the same, and we get a 3D plot. We can move it. Now I have my list of evaluations. Why do I compare with the 30 squared? Because I told Mathematica to use a grid of 30 by 30 as a starting point. So what Mathematica did was to create a grid with 900 points. Those were the initial evaluations, and from there it propagated and started adding evaluations to create smooth functions. Back in the days, I think up to Mathematica 5, the grid would be the only evaluations to create a plot. So if you wanted something smooth in 3D, you would go for 100 here. Now it does it adaptively, which means that Mathematica now it's much slower than it used to be. Why? Because it creates smoother or nicer plots. So I have these 25,000 evaluations. I can put them into my three-dimensional space. Here they are. So these are only the evaluations. There is no texture. So these are just points. And I can put everything together except for the fact that something crashed. No? Okay. All right. So I can put everything together, and then, as usual, show does everything for me. And now I have the surface as well as the points. And you see the same story. You see that along these faces there are very few evaluation points, and on the crest, on the ridge, there are plenty. I think I'll stop here. Just the last thing is that you can animate not only with manipulate, but there is also animate. Okay, this is the difference between a grid and the automatic auto smoothing. Okay, let me just finish with animate. Animate is not as nice as it used to be because now it asks too much to the processor. Basically, it computes everything on the fly. I very much liked to compute all the frames one after another, and then I could just put them together. And nowadays, I'm not sure you can do that anymore, but there is animate. All right, guys, I'll see you on Tuesday.